guys, welcome back to the LearnAPChem series here at LearnAP. In this video we're going to talk about intermolecular forces. So we'll go over dipole-dipole forces, London dispersion forces, instantaneous and induced dipoles, and hydrogen bonding. As usual guys, if you have a question on any of this stuff, be sure to leave a comment, or you can ask us in the weekly live streams we do every Sunday from 5 to 6 p.m. Eastern. Alright, so other than that, we'll get started. Alright, so let's start by talking about intermolecular forces in general. So intermolecular forces are commonly abbreviated as IMFs, and these describe the strength of the attraction between molecules. And this is typically in a liquid or solid, but there are IMFs in a gas. Now this brings me to my next point, that IMFs are stronger as atoms get closer together. So they're very present in, say, a liquid, where if this is our atoms, they're closer together, while in a gas, they're going to be spread apart, and even closer in a solid. So here our IMFs are weak because our atoms are spread apart. But here, and this would be like a liquid or a solid, this is a gas. And so here, when our atoms are further apart, our IMFs are weaker. So that's why we see IMFs talked about in liquids and solids, but not really in gases, because our atoms are so spread apart. Now, I'm going to talk about different IMFs, but these can all be sort of categorized or referred to as van der Waals forces. Alright, so let's talk about the first kind of IMF, and these are dipole-dipole forces. Now note that these only exist in polar molecules, and to understand why, you have to understand that polar molecules are sometimes referred to as dipoles, meaning that there is one positive pole and one negative pole. So looking at the word di meaning two, pole, so literally two poles. Of course, one being positive, one being negative. So dipole-dipole is describing the attraction between the dipoles of a compound. So if we look back to H2O, or water, I know that we have these dipoles where oxygen is sort of hogging my electrons, and so oxygen becomes a negative dipole and the hydrogens become a positive dipole. Now dipole-dipole forces talk about the attraction between these dipoles. So if I have two water molecules, my dipole-dipole forces refer to the attraction between these positive dipoles and the negative dipoles, and vice versa. Now note that these only exist in polar molecules. So say if I had H2, I don't have any dipoles on this atom, so there's no dipole-dipole forces. The force of a dipole-dipole can be described by equaling the strength of each dipole all over the radius squared. So as our radius between becomes bigger, our force goes down. Similarly, as the strength of our dipoles go up, our force is going to increase. Now, dipole-dipole forces exist in the liquid and solid state, again because the atoms are closer together. If we're in a gas, if you think about it, what's happening here is that our R has gotten really big. So right here, our R has gotten very big, and so we're going to see a very, very small force. And just a quick note, the strength of our dipole-dipole forces often define properties of a compound. So just something to keep in mind. Alright, so now let's talk about London dispersion forces. Just a quick note that in general these are weaker than dipole-dipole forces. But unlike dipole-dipole forces, these happen in all compounds and atoms. So let's take a look at what this is. A London dispersion force describes the improper configurations of electrons around an atom or a compound. So take, for example, we'll say carbon. If I draw an electron cloud, so these hyphens represent electrons, so 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, if, say, 4 of these electrons were over here, and remember that this can happen because electrons move randomly, I have sort of this negative charge over here and a positive charge over here. And this is the essence of London dispersion forces. These are also referred to as dispersion forces, instantaneous dipole forces, and induced dipoles. And the reason for that is, let's think about having another carbon compound. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Sort of perfectly oriented. If this dipole happens, or I'm sorry, not dipole, if this dispersion happens, this positive charge is going to sort of pull electrons this way. So now these 4 are going to go over here. And now we can see we've sort of induced this dipole here. And so that's why it's called an induced dipole. And that's sort of the concept of how that works. Now note that these are instantaneous, and they're only lasting for a very, very short period of time. Another concept to be familiar with is polarizability. So let's take, for example, helium, which has 2, and we'll go again with carbon, which has 12. So here, helium won't really be polarizable because of a lack of electrons. Well, carbon will. If helium forms sort of this instantaneous dipole, this is only going to be sort of negative. Well, if carbon did it, it would be, it would be sort of much more negative. And so this is the concept of polarizability. If something has more electrons further away from the nucleus, it is going to be more polarizable, meaning that these dispersion forces will happen easier and that they will be stronger. So note that more electrons means more polarizable, means stronger London dispersion forces. Alright, so let's talk about another type of IMF, hydrogen bonds. Now, you can think of hydrogen bonds as a very strong dipole-dipole forces. And they're called hydrogen bonds because normally hydrogen is involved. So taking water, for example, I said earlier that this is dipole-dipole, which is true. But more specifically, this is an example of hydrogen bonding. Since hydrogen isn't very electronegative, atoms having hydrogen covalently bonded are going to be much more polar, because this oxygen is going to have an easier time sort of stealing the electrons from hydrogen because it's not very electronegative. And so this creates a very strong dipole-dipole force, and it's known as hydrogen bonds. And so these are going to be sort of much, much stronger than your normal dipole-dipole. And they work the exact same way. The only thing to know is that they happen with hydrogen and that they're much stronger than a normal dipole-dipole force. Alright, so that brings me to today's challenge problem. If an atom has stronger IMFs, would its boiling point be higher or lower? So usually we put up a practice solution on our website, but for this one, we're just going to talk about this in the next video. So sort of think about, if an atom has stronger IMFs, would it be easier to boil off into a gas or harder? If you guys found this video helpful, please like and be sure to subscribe for future content. You can like us on Facebook or follow us on Twitter for updates about new videos and our live streams, which are every Sunday from 5 to 6 p.m. Eastern for AP Chem. Links for that stuff will also be in the description. Leave a comment if you're still confused about anything, or also any other comments on the video in general. Other than that, I want to thank you guys for watching, and I'll see you in the next video.